Welcome to the beginning of Unit 4 on forces. So our first three units really looked at how things move. So kinematics, acceleration, velocity, and studying that stuff. Now we're going to talk about why things are moving, which is dynamics. The fundamental idea here is if an object's motion changes, what causes it to change is a force. So in other words, a force will cause acceleration, and we'll see where that pops up when we get into Newton's laws a little bit later on. But that's the big idea, that if we have some force, it's going to cause our object, whatever it is, to accelerate. Now the question is, what is a force? Now a force is very simply defined as either a push or a pull. That's very, very basic. It can be a lot more things than that, but typically if there's a force, one of those two things is happening, either indirectly or directly. It is a vector, so it does include direction, and its units, as we've seen already in a couple of different problems, are newtons, which is a capital N. There are two big categories of forces. Contact forces, field forces. We're way more familiar with contact forces in our everyday life because that's anything that has physical contact. So if you're pushing something, say, a box, or carrying your bag, anything that involves physical contact, friction, because that's just two things rubbing together. That's a physical contact, is a contact force. Field forces, on the other hand, do not require that physical contact. There's one of them that affects us every day, which is the biggest example, which is good old gravity. Then one other one that's very, very common, though we forget about it a lot, would be magnets. So magnets, they don't need to be in contact to feel that attraction to each other. They become contacted sometimes, but they don't need that contact to feel the force. So, a little bit about forces. Now let's do a little bit of history. We talked about history between Galileo and Aristotle once before. Here it comes again. Kind of the same outlook. So Aristotle, the harder you push on something, the further it goes. Logically, true. So the greater force, greater distance, and the object will keep moving when you apply the force. And this is what we see. But there's some fundamental ideas here that Aristotle did not investigate. Galileo did. Aristotle was wrong again. What Galileo said was that there are other forces other than just ourselves pushing on it. So something like friction is what stops it from moving. So that's just a different force. Because what Aristotle would say was it would stop because there's no force being applied to it. Even though we know when you push on something, it moves a little bit but slows down because friction is slowing it down, which is just another force. And so if you could remove friction, this is what Galileo theorized, then an object would keep moving. And that's kind of a little bit about the history of forces. The biggest part of forces comes in when we bring in Newton's laws. So that's when forces really got defined. Galileo still really didn't come up with big accomplishments when it came to forces. Before we get into problems, we have to know what we're looking at. When we're looking at forces, we will always draw a free body diagram. What a free body diagram is just a basic picture that shows what forces are acting on our object and what directions it goes. So we have Bob pulling on a crate and Jim pushing on a crate. And friction on the floor is pulling it back. What would a free body diagram? So a free body diagram is always very simple. It is not drawing a diagram. You just draw a simple square. And then you draw the forces that are acting on it from the center of the square. So we've got Bob pulling this way, so the force of Bob. And then we've got Jim pushing on it. Now, it says arrows are coming out of the box. So we are not going to draw it pointing into the box. We're going to draw it on the same side as Bob because it results in that same direction, even though he's pushing on the other side of the box. And then friction, it says, is pulling it back. So we've got F here of friction. There are other forces on this, but we will learn about them and introduce them in time. But for now, these are the forces that we need to worry about on this diagram. So let's always labeled with symbols, no numbers, and it's always from the outside rather than pointing in. So let's take a look at a few examples. A book being pushed along a table. So doesn't give us a direction, so we can arbitrarily choose a direction, and I'm just going to say that we've got the force this way. Now for an applied force, when we don't have anything specific, we just call it a force applied with this, so that gets a subscript A. And if we're thinking about real life, that means there's also friction here. So this is typically given FF. Now a car accelerating at a stop sign. So that means it was at rest. Again, we're going to have an applied force. That applied force comes from the engine. We have an applied force. We are going to have friction. The tires are on the road, so there is friction. It's the same forces. A lot of times these problems have the same forces. Even though they might be different values, the free body diagrams will be very similar. An egg falling from the balcony. So we've dropped an egg. Forces that are acting on it, a little bit different. It's not an applied force because we're not, it's not giving itself a force, but it is being pulled down by gravity, which we label as Fg. We don't know anything about this problem, so we have to assume it's in the real world, which means there's also something that resists it. So force of drag, so like air resistance, slowing it down. So we've got forces all different directions, but if you notice, we're always drawing our arrows outwards, not inwards. Okay. The whole point of this is to come about the net force. The net force is the key to solving all of our problems. So we've got the same situation with Bob and Jim, but this time we're given numbers. So Bob is pulling with 12 newtons and Jim is pushing with 11 newtons, and the friction is 8 newtons. What is the net force? Net force is just adding up all the forces together, but we have to take into account the directions. So it's the vector sum. So we're dealing with vectors here. We're not given directions, but if you remember back to the diagram, we knew which way they were drawing. So I redrew the free body diagram here so we can see it, because that's part of our problem always. List what we know: Jim, Bob, force of friction, and net force. We want to make these vectors because forces are vectors. A lot of times we just deal with them as not vectors, but they are vectors. So we would write our problem like this to start, that we are just adding the vector versions of all of our forces together. We have not accounted for any directions yet. Our next step accounts for the directions. So then we're going to get rid of our vector signs, and we're going to give things positives and negatives based on the directions. The direction that we're moving here is to the left. So what I want to do is I'm actually going to say that this way is positive, so that our Jim and Bob forces stay positive, so they are F positives, but then our friction becomes negative. So we get this. So now we've dropped our vector signs, added in our directions, so we have that one negative because friction is to the back. And now we got to put in our numbers for Fj, Fb, and Ff. So we've got 11 newtons plus 12 newtons minus 8 newtons. And so 11 plus 12, 23, minus 8 is 15 newtons. And that's our F net. So we're just adding up our forces, figuring it out. Calculating F net is the key to every problem in forces. If you're not calculating F net, you're going to do something wrong. So here's just a couple of steps that went through that again, and there's some textbook questions to practice there. Now let's talk about the first law. The first law is an easy one. Isaac Newton came up with these, and it's just built on what Galileo said. So the first law, you see in the workbook there, you can read more about it on page 103 to 104. A body in constant motion tends to stay in constant motion, and a body at rest tends to stay at rest. What does that mean? What we're talking about here, so constant motion, that means acceleration is equal to 0 meters per second. So that's a key here. So Newton's first law, acceleration is 0. Doesn't say that, but constant motion implies that our acceleration is 0. So what are things that help apply Newton's first law? So if we think about the tablecloth trick, pulling a tablecloth and the objects on top of it staying where they are, that's, you pull the tablecloth fast enough, the glasses on top will stay there because they are objects that want to stay in the state that they are, which is at rest. So if you pull slowly, you won't have that same effect, but if you pull fast enough, the object will stay where it wants to. If objects in motion want to stay in motion, so that's one example. And another example is if you're in a car, the reason seatbelts work is they hold you in the seat. When a car stops, your body wants to keep going forward. That's why you have that sensation of going forward and you feel the seatbelt pull you back. Your body wants to keep moving like it was, and the seatbelt holds you back. So seatbelts work to stop the first law from happening because you would want to keep going and eventually go out the windshield in a serious accident. So, two cases though. We said at rest and at constant velocity. We have to think about those things being the same thing. And that's important to think about. And we talked about this before. So they are the same thing. It all depends on your frame of reference. So, in terms of forces, it doesn't say that there are no forces, but the net force is 0. The forces are all balanced. So, that's like if you're saying we're pushing on something and it's not moving. There's forces, but they're balanced, so it's not going to change. And this comes up to another important idea, which is why this law is often connected to the word inertia. The tendency of a body to remain at rest or move at a constant velocity is called inertia. And this is something that how much an object resists its change. The more inertia, the bigger the object is usually. So, a couple examples. We can think about pushing a chair with a 25 kilo child or a 75 kilo adult. Which one's easier? The 25 kilogram child. So it's easier to push that because it resists change less. We'll start to see how inertia and mass come into effect when we talk about mass and weight. Another situation I mentioned briefly was pushing a box, but it doesn't move. So we're pushing on it this way, so we've got force applied, but it's not moving. So that must be that there's a friction force stopping it, and Newton's first law is always that the F net is 0, which means Fa has to equal F. So if those two forces balance each other, then we have no motion and the object stays at the position it is in. So there's a couple of workbook questions there. So that's free body diagrams and Newton's first law, two big ideas for this video. And as always, physics is awesome.